Hi guys, this is 6.06 free body diagrams with centripetal force. So in 604, we talked about centripetal acceleration. In 605, we talked about centripetal force. And we said that any one of our categories of forces can act as centripetal force. So in this first problem, what we're going to see is that it's friction that is providing the centripetal force. In our second problem, we're going to see it's tension that's providing our centripetal force. And our third problem is also tension, but gravity can be a centripetal force. Normal force can be a centripetal force. So the centripetal force is not a force by itself. It is one of our contact forces or gravity that causes circular motion. The other thing we said was it is always directed inwards towards the center of the circle. So what I did was I have three problems here. The first problem is a little simpler. And the next two are problems that were really kind of tough. And as I was going through, you're going to be doing a lot more multiple choice starting this chapter going forward. I pulled out the problems that were really kind of difficult. And I thought I'll use those as sample problems so that you get some good explanation at the front end. And you're not quite so stumped when you see those come across your multiple choice. This might be done in two parts, so I don't have it listed as part 1 and part 2, but I'm keeping track of the time. And if my time starts to go long, I'll split this out into a second part. So let's look at problem number 3. This is out of your student sample pack, so you have these copied off. If a student rides a bicycle in a circle at a constant speed and constant radius, a force diagram for the student bicycle system is shown above. The value for each force is shown in the figure. What is the acceleration of the student bicycle system? So this looks like a regular free body diagram, but if we could see this, the motion's circular and it would be coming up out of the paper and going back down into the paper. So we're getting a side view of this student riding his bike around the curve on, maybe he's going around the track. I don't know. So because he's moving in a circle, he's moving at a constant velocity. So you would right away say, oh, he doesn't have acceleration. But remember, when we're going in a circle, we're changing direction constantly. So even though I have a constant speed, I still have acceleration because I'm changing direction because I'm moving in a circle. And the force that's allowing him, now, if all of a sudden this friction disappeared, this kid would just go flying off the circle, tangent to the circle. We saw if you don't have a force moving you in a circle, you just shoot off in a straight line. But because we are moving in a circle, we see that this force of friction is what is supplying the centripetal force. So in this case, centripetal force or FC is supplied by friction. And we know that FC, so force is equal to mass times acceleration. In this case, though, AC is going to be centripetal acceleration. Centripetal acceleration. Now, sometimes we'll want to use the expanded form. We know that centripetal acceleration is tangential velocity squared over radius. But in this case, we're not going to need that. So what they want to know is, what is this? They want us to solve for AC. Well, we know that our centripetal force is 250 newtons. So we've got 250 newtons is equal to mass, and we're solving for AC. Well, they didn't give us mass. Take a second and pause the video if you need to and see if you can figure out where mass is going to come from. All right, did you figure it out? We know that the force of gravity is equal to mass times gravity. Whoops, I'm off screen. Mass times gravity. So if that is equal to 500, we know that acceleration, that should be acceleration due to gravity. Let me rewrite that. We know that that's 10. So if we take 500 divided by 10, and a lot of times on the AP test, that's where these questions came from. They'll approximate gravity to be 10. That's going to give me a mass of, so my mass is equal to about 50 kilograms. Now I can bring that up here. and I find that my centripetal acceleration is about 5 meters per second squared. Okay, so that was our first problem. Let's go on to our next problem. Problem 4, and I'm going to leave plenty of space. Yeah, space above there. Again, you'll notice there are just tons of diagrams, and that's to, let me see if I can focus this any better. That is to eliminate any ambiguity in the problem. So we have a solid disk of diameter d, spins counterclockwise about its center at a constant speed. One end of a string length L is attached to the edge of the disk with the other end attached to an object of mass m. As the disk spins, the string makes an angle theta with respect to the vertical, as shown in figure 1. A force diagram of all the forces exerted on the object at time t are shown in figure 2. So it's really difficult, for me at least, it's difficult to kind of figure out what's going on here. The best I can understand it is this circle is coming up out of the page in a circle and going back down, and it would be moving this direction. And it's with this angle to the vertical. I really like figure 2 because that really helps me out. Okay, so here's my ball, and I've got the force of gravity, and I've got tension. They already give me my 3-body diagram. And they're saying this is the direction of the centripetal acceleration. Well, right now, it doesn't look like I have any vectors going in the direction of centripetal acceleration. But remember, when we have vectors that are not on our coordinate system, so in this case, we have, we'll call this is positive. We have to resolve them. So we're going to have to take this vector t, and I'm going to just cross this off, because I want you to understand that this is t. I want to break this into tx, and I want to break this into ty. And I have my angle of, so I'm going to pause the video 1 second. Okay, sorry, I had a phone call there I had to take. All right, so we've got ty, we've got tx, and we've got theta is here. So we could say that ty is going to be equal to, we know that this is going to be a cosine function because this is adjacent. So we're going to say ty is equal to t cosine theta, and we're going to say that tx is equal to t sine of theta. So it looks like our centripetal, I'm going to grab a highlighter or a yellow marker will work. Our centripetal force is being provided by this right here. So if you're going to answer this, you would want to say t sine theta. But if we look at our answers, that's not an option. The other thing is we see two of these answers, they've worked in G, and we've got tangent functions. Well, if you remember, sine divided by cosine is tangent. So that tells me that something's up. And this is why I picked this problem. They could have just said simply, what is the magnitude of the acceleration of the object of mass m at time t? They could have said that t sine theta is equal to mass times acceleration, because this is providing our centripetal force, but they don't. So that means we need to look at this in a different way. So let's keep going with this. We also know that this, I'm going to switch colors here. We know that the force due to gravity is going to be negative mass times gravity. So the other thing I could say about ty is that these are going to be equal and opposite because my motion is here. So I could say this is also equal to positive mass times gravity. So let's look at these equations, and I want to kind of walk through this. So we now have two equations. We've got t cosine theta equals mg, because we know these have to be equal and opposite. And we have that the centripetal force is provided by this. So we can say t sine theta equals mass times centripetal acceleration. All right, well, we've got interesting things. And here's that sine cosine. Here I've got mass, or I'm sorry, I've got gravity. So this is telling me that to get to here, I'm probably going to have to do a substitution of equations. They want me to find the magnitude of acceleration in terms of both of these. And when we get to the end, I think you'll see why. So the first thing that I'm going to do is I'm going to take this value, and we're going to do a substitution. So let's say that, let's put this in terms of AC. Let's say AC equals T sine theta divided by M. So I divided this side by M and that side by M, and I put that in terms of AC. And I'm going to put this in terms of M. I'm going to say that T cosine theta, whoops, is divided by gravity, not M, sorry. So don't get too freaked out, because all I'm doing here is algebra. I've got some fancy algebra going on. All right, now I'm going to substitute this into that. So I now have that the centripetal acceleration is equal to T sine theta, and I'm going to put divided by, I'm going to put this over 1, divided by T cosine theta over G. And remember, when I divide, I have to flip and multiply. So that's going to be AC is T sine theta over 1 times G over T cosine theta. That's going to give me, I'm going to come down here, centripetal acceleration is T sine theta G over T cosine theta. All right, so here, my T's cancel. Sine over cosine is tangent. And I multiply that by G. So it turns out that my answer is going to be letter D. So let's talk about what we did here. First of all, I came up with an equation that was unique to this situation by combining my horizontals and my verticals. I could find out what my centripetal acceleration here is without knowing my mass, without knowing anything other than the angle. All I need is the angle, and that's going to give me my centripetal acceleration. So anytime you now know, anytime you have an object that has an angle to the vertical, and the centripetal force is supplied with a partial this way and a partial that way, you could use gravity times tangent of the angle. The second thing we did was we took a situation and we created a new equation. AP test loves creating new equations, and they ask you to do that all the time. And we're going to do that in the next problem as well. So in this example, what is the magnitude of the acceleration? And I don't think it ever gives us theta, so we don't find an answer, but we do find it in regards to what the problem gives us. So again, our takeaways here are specific to centripetal acceleration, that this equation is a good one to have in your banks. And the second thing is we got some practice doing formula derivation. Now, we started off with a regular free body diagram where we had to break our components, and we had to do an analysis of the horizontal to vertical. Last thing I want to add is you'll notice I didn't do a motion vector. That's really hard to do when we're doing circular motion, especially it's implied that it's coming up out of the page and going into the page. So I did not do a motion vector here. All right, this is getting long, so I'm going to break here and do the third problem in a part 2. All right, to be continued.